The last topic for our section on energy is power. And power really is, we'll run into the word power in a lot of different contexts in this class and in other physics classes. It just means how much energy is moving per unit time. Okay, and so we'll talk about all different kinds of energy changing over time. But power, as a broad definition, just means how much energy is being used or transferred per second or per minute. So those are two kinds of potential energy. We want to also talk about how quickly work is done, and this is called power. So power is actually defined as work per unit time, or change in energy per unit time, and this is a watt. Um, so we could combine a bunch of equations. These are all, um, just taking basically our work equation, FD cosine theta, and throwing it into this equation. So we could use this. We don't use that a ton. Mostly we're interested in this guy here. So usually you'll find work and divide it by time. But what does power matter? How is it different than energy? Well, let me give you two examples. In automobile alternative fuels, something like a fuel cell, energy content matters a lot. How much energy can I store in my battery? But if you can't release that energy quickly, then your fuel isn't going to work very well for powering a car. Gasoline is really good, right? It's explosive, literally. And that means it's able to turn its energy into kinetic energy very quickly. Some of these others are less good at that, and that makes them less desirable as fuels. So it matters not only how much energy you have, but how quickly you can get rid of it. In sports, power, you hear talk about power a lot, right? You can be super strong, okay? But if you can't release that, you can have a lot of energy in your muscles, but if you can't release it quickly to swing your bat or to jump up in the air, then it's going to be less useful, okay? So not only you can have an amount of energy that you can use, but you have to be able to use it quickly, and that's why power becomes important. So let's talk a little bit about power. One of the horsepower, you probably heard that as a unit for power. So let's do a little conversion thing. So we have a 100-kilogram person who runs a distance of 4.9 meters up a flight of stairs. In what amount of time must he make it up to require 1 horsepower? Okay. Well, power is defined as work per unit time. Now, we can look at all sorts of different ways of doing this, and this is a common problem, deciding whether to use work or to use change of energy. Here we don't know our force, right? We could do FD in this direction, but we don't know what the force is. So what do? Well, we have potential energy, right? We have a height difference. We know that there's a mass here, and then later that mass is here. So we can calculate our change in potential energy, right? Work done to this body is the same as the change of potential energy. That's what work is. So we can move easily between those two worlds. So energy here is equal to change in mechanical energy. And since we're stopped at the bottom of the stairs and stopped at the top, we don't have any kinetic energy. So all we need is delta PE. We know our equation for delta PE, and we have to define delta H, right? So here we're going to have to use our SO, CA, TO. We know 33 here. This guy is the opposite, so we're looking at so we want to use sine. Here's our hypotenuse of 4.9, and we find that he goes up by 2.7 meters. And then we can calculate the change in potential energy, mass, gravity, change in height, and get a change in potential energy of 2620 joules. Now, if we want to know what the power is, we want to find the time to mean that he used 1 horsepower of power in order to get up that height. So we know that power equals delta E over delta T. We want to find delta T. Okay, and we know the other two. So delta T equals the change in energy divided by the power. HP is a British unit, and so we want to convert between watts and horsepower. So we'll multiply by unity, right? We want to get rid of our joules, and we want to get rid of our horsepowers. So that works out very nicely. And it's going to leave seconds, right? And so we find 3.5 seconds. So that gives you an idea of what a horsepower is if you're interested in that. You know, here a car has 400 horsepower or whatever. 1 horsepower can move 100 kilograms, a fairly large sized person, up 3 meters, which is about 10 feet, in 3 seconds. So that's not an insignificant amount of power. And so when you talk about 400 and 500 horsepower, that's a pretty big number. Okay, so let's sum up our main terms here. And that's force, work, energy, and power. Force is the thing that compels acceleration, right? That's Newton's law. When it moves matter in the direction of a force, it's doing work. Okay. Work converts energy from one form into another. So if you have some kind of